Now we have already talked about Bohr's model of hydrogen atom and the basic assumptions of Bohr's model, where that nucleus was assumed to have the infinite mass, and probably nucleus was considered to be at rest because it was assumed that its mass is infinitely large. But this assumption is not true. Uh, in real world, we have finite nuclear masses, and it was Bohr that he corrected the term of mass that's involved in the expressions that we have obtained for hydrogen atom or hydrogen-like atoms. Now the point here is that I would like to discuss this correction. This correction was made by Bohr himself to introduce the finite mass of the nucleus and and to have the expression for energy, the expression for radius, and all of those things that we have talked about in the previous video. So what was assumed there was that the mass of this nucleus is infinite. So we have obtain an expression for the Rydberg constant. And here I would like to write that Rydberg constant as R infinity. And infinity is a kind of symbol here to indicate that uh, that 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 the mass of the nucleus considered in this case is infinite, and nucleus is assumed to be at rest with respect to the motion of the electron. So it's only the electron that's revolving around the nucleus. So here we calculated this Rydberg constant, and it was m e to the power of 4. I think it would be right to introduce e here. Me will refer to the mass of the electron, and divide by 8 epsilon naught square h cube and c. So this is the value of Rydberg constant for hydrogen atom, and uh, and and what's assumed here is that the mass of this nucleus is infinite. But the atoms in reality, the nucleuses in reality have the finite masses. So they have finite masses. Now, if that's the case, then we have a situation like this. What we have electron and we have the nucleus. Now, let me assume that the mass of this electron is me and the mass of this nucleus is mn. Now, since this nucleus has a finite mass, so what's going to happen here is that the rotation will be with respect to their center of masses. Suppose this is the point of center of mass. So let us assume that uh, this is the state of rotation. Now uh, this system of an electron and the nucleus, they will rotate on a common axis of rotation, and this will refer to its center of mass. Now, if I assume that the distance from this center of mass, if I assume that this distance is, say, RE, and the distance from center of mass to the nucleus is Rn. So Me is mass of electron, Re is the separation from this center of mass to the electron, Rn is the separation from center of mass to the nucleus, and Mn is the mass of the nucleus. So what we are dealing here is we are dealing here with what's called as reduced mass. Reduced mass. And there is one more important thing, that is that this MERE is MNRN. So the relation that we have is that this Me by Mn must be equal to Rn divided by Re. So this R will be farther from this particle. If it's a particle, say for example, it will be farther if the mass of this particle is small, and if the mass of this particle, taking nucleus into consideration, the mass of this nucleus is large. So owing this relation, the separation from center of mass to the nucleus will be small. Now, what we have here is reduced mass, and what is that reduced mass? What we have here is reduced mass. I'll write it again: reduced mass, and that's symbolized as mu, and that is equal to mass of electron, mass of nucleus, divided by mass of electron plus mass of nucleus. Okay, that's the important thing. Now we have a system in which we have the motion of electron and we have the motion of the nucleus, and me and mn, and there we have this axis of rotation with respect to the center of mass. Now, the important point is here that the overall magnitude of angular momentum. So, what will be the magnitude of angular momentum? If we rightly remember, in case of Bohr's model of hydrogen or hydrogen-like atoms, the quantum condition comes in terms of angular momentum, and what is assumed there is that the angular momentum is quantized, and this angular momentum is basically equal to the integral multiple of angular momentum. What is that? That's mvr, is integral multiple of h pi 2 pi. But the point here is that we have m, and m refers to the mass of the electron. But here certainly what we have assumed that nucleus is at rest because of its infinite mass. So here what we have is the magnitude of this angular momentum will be the sum of angular momentum due to the electron and the angular momentum due to the nucleus. So this Le is, I assume that this Le is the angular momentum of electron, and this Ln is the angular momentum of nucleus. So what can we do here is we can write down the angular momentum of electron. That's me, ve, and re. That should be clear. So this is my re, and this is my rn. Okay, and plus mn, vn, and rn. And what we have is we have a relation between linear velocity and angular velocity. And what's that? V is r omega. So r is it is the radius, or you can say the separation from center of mass to the particle. So V is r omega, means VE is RE omega, and VN is RE omega. And we better understand that the angular velocity is not going to change. Omega will remain same for this kind of rotation with respect to the center of mass for both electron as well as nucleus. But certainly their linear velocities will have different values at different points depending on the separation from this center of mass. So I would like to introduce this VE and VN in this equation. So what will I get? I'm going to get L is ME. Instead of VE, I'm going to write omega. RE times RE will give me RE square plus MN V, not V, omega, then V RE square. Here I have written it wrong. This is Rn. Okay, so here I have written it wrong. Here it is Rn whole square because of using these two equations. So moving on from here, what we have now is this L will be me omega Re square plus mn omega Rn square. All right. Now let me try to develop a case here. What we have is, as I have written down that equation already, where I showed that this MERE is equal to MNRN. If I write down this equation here, what will I write? I will write E by Mn is Rn by Re. Okay. Now I'll call this as equation 1. And in this equation, equation 2, I will add 1 on both sides. What I'll get is Me by Mn plus 1 is Rn by Re plus 1. So here I'll get Mn. So this is Me plus Mn. And here I'll have in the denominator Re. Here I'll have in the numerator Rn plus Re. That should be clear. Okay, so so if we look at this Rn and Re, when we add the two separations from this center of mass, this is equal to this total separation. Let us assume this total separation is R. Okay, so Re plus Rn, I can write it in terms of R. Okay, so what will I get here is Me plus Mn divided by Mn is R divided by Re. Okay, so now what would I do? I'll call this 3. I'll substitute this 3 in my equation 1. And similarly, what will I get? Here I have got basically Re. Let me write down that Re first. So what is Re? So Re will go up. So here I will have Mn divided by Me plus Mn times R. So similarly, what will be my Rn? That will be Me divided by Me plus Mn times R. Okay, that should be the case. Now, this is my, say, equation 4. This is my equation 5. And I would like to substitute this 4 and 5 in my equation 1. Okay, so what will I get here is substituting 4 and 5 in 1. Okay, what I'll get? Okay, I'll get, yeah, what I have is L is Me omega Re square. So here I'll put it here. So this I'll give me, it will give me L is equal to, yeah, that is, what is it, gone? So Me omega times Re square. Re, we have calculated that. That is Mn divide by, so this is Mn square divide by Me plus Mn. This is whole square. And then R square. Plus, then we have Mn omega Rn square. So we have Mn omega Rn, instead of Rn, what I have, it is Me by Me plus Mn whole square and R square. That should be the case. All right. Now, so what can be the common here is I can write down here omega is out. Okay. Omega is out, and then what I have is m. This is gonna give me, this is me, and this is, yeah, am I doing it right here? This is yeah, so omega is correct, omega is out. So yes, so what I'll so this is me, and let me get it out, me, okay, then mh, if I get it out, what will be inside? Inside I'll have m, it's not h, it is n, keep that thing in mind, the mass of the nucleus. So here I can write mn, okay, plus okay, m is out, so here I can write m e, okay, this is whole divide by me plus mn whole square times r square. Okay, now this mn and me, this is going to cancel with the square here. So what will be left, we'll get L. So L is going to be me mn, then omega r square by me plus mn. Now, what is this? me mn by me plus mn. This is nothing but reduced mass. This is mu. So L will be mu times omega r square. So this will be our angular momentum of this system of electron and the nucleus, and 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 to move on from here. So this correction was basically this correction was done by Niels Bohr himself. He made this correction himself, and 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 the quantum condition that was given by Niels Bohr, it had to be modified by replacing the mass of electron by the reduced mass. So, so this orbital now, this L is not the orbital angular momentum of the electron. This L is the orbital angular momentum of atom itself. So, so the Bohr's quantum condition is modified. What would be that quantum condition? That the orbital angular momentum of the atom, that is mu Vr, is nh by 2 pi. Okay, this n is an integral number. Its values can be 1, 2, 3, and so on so forth. And this h is the Planck's constant, right? And the mass m that was used in case of hydrogen atom and hydrogen-like atoms, where it was assumed that the mass of the nucleus is infinite. That mass is replaced by this reduced mass. And if we rightly go back and write down the energy of the energy of this system of hydrogen or hydrogen-like atoms, it is minus z square by n square times m. It is m e to the power of 4 by 8 epsilon naught square h square. All right, so this m has to be replaced by mu automatically. So E is going to be minus z square by n square times mu e to the power of 4 by 8 epsilon naught square h square. So this is the modified energy. This is the energy energy of the system, that's in which we have replaced the mass of the electron by the reduced mass of the system of electron and proton. All right, and so what could we expect from here is the Rydberg constant that we had calculated for hydrogen atom or hydrogen-like atoms. This Rydberg constant is not going to be same now. It's going to have different values for different atoms because now we are assuming finite nuclear mass. Assuming the finite nuclear mass certainly gives us the mass number, and mass of the different nucleuses. This reduced mass for different nucleuses or different atoms is going to be different. So that means the value of Rydberg constant for different atoms or hydrogen-like atoms is going to be different. It's not going to be the same. Now, if we go back to that Rydberg constant, so what we assumed there is the mass of the nucleus is infinite. So let me write down that Rydberg constant as R infinite. And what was that? That was m e to the power of 4 divided by 8 epsilon naught square h cube c. This is for assuming infinite mass of the nucleus. Mass of nucleus. Uh, and what will be Rm? This is going to be the Rydberg constant of an atom in which we assume that the nucleus has the finite mass. So here we will have mu e to the power of 4 by 8 epsilon naught square h cube and c. So here what we have finite mass of nucleus. So this thing should be clear now. So R infinity is an indicator of the fact that it was assumed that nucleus is momentarily at rest because of its infinite mass. Now, if we take the ratio between these two, so dividing the two will give me R infinity by Rm. Every term here is same. All the terms are going to cancel, and we will be left with mass of the electron here and the reduced mass. Okay, so let me write down this as mass of the electron. So I'm going to write down here is mass of electron divided by mu. So, what does this mean now? This mu is what? It's the reduced mass. Okay, this reduced mass is going to be less than that of mass of the electron, because if we go back to that equation of reduced mass, we have mu is equal to mn by me plus mh. Now this reduced mass is less. Okay. Now if this reduced mass is less, that means mu is less than this me. Now if this is less than me, that means this me by mu is less than 1. So if it is less than 1, what does that mean? That means this Rm or m. Am I right here? R infinity. Let me take it in the opposite sense. I'm doing it wrong, I think. So that way it will be simple. So this is R m divided by R infinity. That is mu by mu e. Now, using this condition that mu is less than me, this is going to be less than 1. So this implies mu by mu e is less than 1. Now, if this is less than 1, that means Rm is mu by mu e times R infinity. So what we understand here is that R infinity is the maximum value for the Rydberg constant. We cannot have the value of Rydberg constant greater than that of this R infinity, because when we assume the finite mass of the nucleus, the Rydberg constant comes out to be less than that of uh, R infinity. So this point should be clearly noted out here, and let's make a more simplified version of it, and if we go and write down this uh, reduced mass. Now what I have is Rm by R infinity is it is mu uh, it is mu by me. Now, what is mu? Mu is basically it is mass of electron, mass of nucleus, divide by mass of electron plus mass of nucleus. So me will come here. This me and me will cancel. So what can I write? I can also do one more modification. Rm by R infinity is it is mn by the mass of the nucleus. I will write here 1 divide by 1 plus me by mn. This will be the more precise way of writing it this way. So we can see here. So this me is the mass of the electron, and mn is the mass of the nucleus. Now this R infinity, what's its value? Its value is 109737 centimeter in inverse. Okay. Now let us assume for the hydrogen atom, where we take the finite mass of the nucleus. Finite mass. So taking the finite mass, what we will have is the mass of electron by mass of proton. This ratio is 1 by 1836. So we can use this ratio in this equation, and we can calculate the Rm for the hydrogen atom, where we consider the finite mass of this of its nucleus. So Rm here is going to be it is 1 by 1 plus 1 by 1836 times R infinity. So when we boil down these numbers, what we get Rm comes out to be 109677 centimeter inverse. So what we see here is that this Rm is less than R infinity. So the value of the Rydberg constant that we have is less than R infinity. Now, certainly, so we will have different Rydberg constants for different hydrogen-like atoms. And uh, in that case, what we say here is that this Rydberg constant it's constant for a particular atom, and its value goes on varying. Now, if I roughly plot the graph for this Rydberg constant, taking this axis as mass number, and taking this axis as Rydberg constant for the particular atom, and choosing the numbers based on these numbers are infinity and so on in the divisions of 20. Say for example, we start from some 80, and then we will have 100, then we will have 120, and the back number is same. Okay, then we what we observe is a curve like this. And for R infinity, where the mass of the nucleus is considered to be infinite, this is the curve for this. All of them have the same value, but this is the experimentally calculated values of different atoms. And at the bottom of it is H1, and here we have H2, and here we have nearly He2, and here I have He4, and then we have lithium, and then we have oxygen. So this curve is giving us an idea of how this value of Rydberg constant varies as the mass number of the atoms goes on increasing. And we can see the gap between H1 and H2 is large, but as the number goes on increasing, as the mass of the nucleus goes on increasing, then this curve flattens. And this flattening of curve is an indicator of the fact that the mass of the nucleus is infinitely large in comparison to the mass of the electron that's revolving against the nucleus.